I'm not going to go intense in anything at this point of time. Just going to give you school related stuff on topics which I have not covered, so that at least you can handle your school properly. We've done our bit on wave mechanics for school. All right. Few things still remain pending, but those are not required for school. So we'll not bother about those things at this point of time. Again, I'll come to problem solving on wave mechanics after a while, but for the time being, I want to give you a kick start on basics of gravitation, right? Which again will take care of your school. Just this is a school related drive almost all of February, and from Feb till let's say mid-March, I'll be very school intensive. I'll also let you free on a few days so that you can at least go to class 12. You bunked the last class. Bunk the last class. Oh, you were there in that room. All right, very calmly, very peacefully. First of all, let me, even in my attempt to teach you for school, I might end up taking a little bit of a detour here and there. Otherwise, the sense of completeness will not be exhibited in the digressions, right? So there would be a mild detour from school related stuff, but eventually it will converge to school. Oh boy, please stop it. Right. First of all, let me define what we refer to as a central force field. A central force field. Let's say there is a point O, and there is a particle P, which in a certain force field undertakes a certain kind of a trajectory. Let's say this is the trajectory that this particle undertakes. While undertaking this trajectory, the particle is at different distances r from a certain fixed point O. The particle is at a distance r, a variable distance r, from a certain fixed point O. And at any given instant of time t, when the particle is here, the position vector of the particle, let's say, is r. The position vector of the particle is r at any instant of time referred to the point O. Evidently, magnitude of r is r. Clear? Now, if a particle is being acted upon by a force which is always along the line joining the position of the particle and the fixed point O, this is a certain position P prime of the particle, right? If the force acting on the particle is always along the line joining the particle to the point O, that means is parallel to the vector OP prime, parallel or anti-parallel, it's the same thing. If the force acting on the particle is always parallel to the vector OP prime, that means the force is always directed along this vector. I would refer to as a radius vector henceforth. The line joining the point O to the position of the particle P, I would refer to as the radius vector, whose magnitude is r, in general different at different points of the trajectory of the particle. Now, if the force acting on the particle is always along R, is always along R in general, what I would say is the force is parallel to the vector R. If the force acting on the particle is always parallel to the vector R, then we say that the particle is subject to a central force field. Then the particle is subject to a central force field, where this fixed point O is referred to as the center of the force field. This point O is referred to as the center of the force field. You know what I'm saying? So that's a central force field. In a central force field, the particle is subject to a force F, whose magnitude is a function of the length R. The magnitude of this is a function of the length R. I mean, it could be R squared plus 2R plus something, and whose direction is R cap. R cap is a unit vector along OP prime. R cap is a unit vector along OP prime, right? So if the force acting on the particle is some function of R into R cap, this R cap would ensure that the direction of the force F is always along the radius vector, is always parallel to the radius vector OP prime. Then this essentially is a description of a central force field. The force always directed towards a certain point O, could be towards O or could be away from O, but along OP prime, parallel to OP prime, parallel or anti-parallel to OP prime, and that's a central force field. Now, some basic traits of a central force field. For example, this FR means a function of R. This F of R could be R cube, or it could be some sin R plus tan R, or it could be some R to power half, or it could be 1 by R squared, or it could be 1 by R cube, and so on and so forth, right? It will be some function of R, right? So the magnitude of the force will depend on this. For different values of R, you will have different magnitudes of the force, but at any juncture, the direction of the force will be along the radius vector, clear? Now, let's say there is a particle which is undertaking a certain trajectory in a central force field. This is the trajectory of a particle in a central force field. And this is the center of the force field. This is the center O, so to say, of the force field. This would be the vector R. Position vector R, whose magnitude is R. If xy be the coordinates of the position P of the particle, at a certain instant of time t, then very clearly, and let's say if this O was the origin 0, 0, then very clearly the vector R is going to be x I cap plus y j cap, yes or no? The vector R, position vector of R of the point P with respect to O, is going to be x I cap plus y j cap, right? A unit vector along R, that is this R cap, a unit vector along R, which is R cap, is going to be x I cap plus y j cap divided by the length R, that's going to be a unit vector along R, right? where evidently r would be root x square plus y square. Distance between O and P, that's the length r. Root x square plus y square. Now, let's say this is the description of the force the particle is subject to. While undertaking this trajectory, the particle is subject to this kind of a force description. In a small time dt, the particle gets displaced by a small amount dr. The particle gets displaced, this was r, the particle gets displaced by a small amount dr. Now, the particle moves in its displacement. It moves from xy to a point q. If this displacement is dr, then small amount of displacement, that means x changes by a small amount, y changes by a small amount. So the coordinates of q would be like a x plus dx, comma y plus dr is what? The vector pq, the displacement dr is going to be displacement in the x direction I cap plus displacement in the y direction j cap, yes or no? So then the displacement dr is going to be dx I cap plus dy j cap, right? Yes? Now, for this infinitesimally small displacement dr, the force vector remains practically the same. The force vector from P to Q practically remains the same because this is an infinitesimally small displacement along the trajectory dr, right? Now, the work done by this force F, over this displacement PQ is going to be F dot dr. The work done by the force is going to be F dot dr. Make sense to you? Which then would be like the F is like a scalar. F of r is a scalar, it's a number. This is a number into a unit vector r cap. So this would be like a F of r cap dot dr. That would be the work done in accomplishing this small amount of displacement dr. That's the work done in accomplishing this small amount of displacement dr, yes or no? Right. Now, this r cap I can write as xi plus yj by r, right? So this r cap and this dr I can write as dx I cap plus dy j cap, right? When I do that, f of r is just a number, different for different values of r, it's a scalar, right? And r cap xi plus yj divided by r dot dx I cap plus dy j cap. Does it sound all right? Now, this becomes like a x dx plus y dy. F of r by r, that itself, this f of r by r would still be a function of r, a scalar, different for different values of r, different magnitudes of the radius vector r, into x dx plus y dy. Now go back to early days in calculus when I told you d of x into x is x into d of x is d of what? Integral of this, isn't it? D of x square by 2. No? You remember this? I mean, if I had like a sine r dr, then that's going to be d of the integral of sine r, which is minus cos r. Right? If I had like a e power r dr, then that's going to be d of e power r. Right? So x dx would be d of x square by 2. Y dy is going to be d of y squared by 2. So then this expression becomes f of r by r d of x square by 2 plus d of y squared by 2. How about it? Which is f of r by r into d of x square plus y squared by 2, right? D of a, change in a plus change in b would be change of a plus b, right? So change of d of x square plus y squared by 2, right? Hey, but what's x square plus y square? R square is r square. So then this becomes f of r by r d of r squared by 2. D of r squared by 2 is r dr, isn't it? D of r squared by 2 is d of r dr. So then this becomes r dr, this r etc. will get cancelled, so that's like a fr dr, that's like a fr dr, yes or no? Okay, where dr is the change in r, is the small change in the magnitude of r. Dr is the small change in the magnitude of r, right? Now, simple thing. Work done over this small displacement is some function of r into dr, right? If the particle moved from a point A where r was r1 to a point B where r was r2, then the total amount of work in navigating the particle from A to B would be sum of all of this, where r runs from r1 to r2, that would be the total amount of work from A to B. So the total amount of work in navigating the particle from A to B would be sum of all of this. R runs from r1 to r2. Now, when I carry out this integration, this f of r had nothing to do with the trajectory. This f of r was at any given r, what would be the magnitude of the force? That would be f of r. What has that to do with the trajectory of the particle? Nothing. F of r meant, f of r could have been r square, and what it meant was when the particle was at a distance r equal to 1, then the magnitude of the force would be 1. When the particle was at a distance r equal to 2, then the magnitude of the force acting on the particle was 4. But that has nothing to do with the trajectory of the particle, right? You know what I'm saying? So in carrying out this integration, r equal to r1 to r2, which is the work done by the force of the field, what is it? This is the work done by the force of the field in enabling while the particle navigates from A to B along a certain trajectory. How? Well, if the particle, instead of moving along this trajectory from A to B, if it moved along this trajectory from A to B, then you'll have the same integral, If it moved from A to B along this, you'll have the same value, right? That means the trajectory details become inconsequential. That means the work done by the force of the field in carrying the particle from A to B does not depend on the path actuals. You know what I'm saying? Work done by the forces of the field to navigate the particle from A to B is not depending on path actuals, details of the path. Is not depending on the path details. If the work done by the forces of the field is path independent, then what kind of a field is it? It must be a conservative field. It must be a conservative field. Conclusion then, that a central force field is unconditionally conservative. A central force field is unconditionally conservative. A central force field is unconditionally conservative. Clear? Now, this is a very important thing to understand. All central force fields would be conservative. Work done by the forces of the field will not depend on how the particle traveled between two given points. What the path actuals were between 2 points. The central force field will care two hoots about that, right? So that's a basic trait of a conservative force. And every time there is a conservative force field, you can associate a potential energy with that field. Go back to work power energy days. I energize you with this thought about conservative force fields. They will always have a property called the potential energy. They will always have a property called the potential energy, right? And in light of this, we even arrived at basics of potential energy commensurate, right? Now, let's say there is a mass m. There is a mass m, right? And let's say this mass is fixed in position. Let's say this mass is nailed in position. In its surroundings, then this mass produces what's referred to as a gravitational force field. In its surroundings, this mass produces what is referred to as a gravitational force field. Any other test mass placed in the region will experience a gravitational force given by gmm by r squared, right? So then, if there is a certain test particle m, undertaking a certain trajectory under the force field produced by capital M, gravitational force field produced by capital M, then realize that if I call this position O and I refer to this position as P, then the magnitude of the force that this particle experiences is G capital M small m by r squared. That's the magnitude of the force, right? Gmm by r squared, which is a function of r alone. This is a function of r alone, yes or no? Not only that, the direction of this force is always from P to O, is always along the corresponding radius vector, right? The direction of the force experienced by this will always be along PO, P, attractive forces, right? Gravitational forces are attractive, so it will always have a force which is directed towards O. No matter where the particle is, it will experience a force which will always be directed towards O. This vector of course is r, so it will be in the minus r direction, therefore always parallel to the radius vector, So then, is the field produced by M not a central force field? The force is always directed towards a certain position O, fixed position O, and has a magnitude which only depends on its distance from O, r, which is r. So, does it not belong to the jurisdiction of a central force field? The gravitational field, is it not a central force field? It is, right? And if it's a central force field, it will then succumb to the requirements of a central force field. It will therefore be conservative. It would then have an associated potential energy with it? Yes or no? Right. Which means now let's say there was a gravitational force field produced by a mass capital M. Let's say there was a gravitational force field produced by a mass capital M. Gravitational force field produced by a mass capital M. Let's say there was another point mass small m at a distance r from this mass capital M. At a distance r from this mass capital M. Now, at this juncture, and let's say this mass is free to move, but this mass is fixed. Alright. So then, the force experienced by small m because of capital M will be leftwards attractive, right? Gravitational forces are attractive, and it will experience a force F leftwards, which is like G mm by r square. G is a gravitational constant which has a value 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared, right? I'm not reiterating those facts. I'm assuming that you're aware of the value of capital G, 6.67 into 10 to the power minus 11 SI units, Newton meter squared per kilogram squared, right? So this is the magnitude of the force, and it's directed towards now, right? Now, if this particle gets displaced to the right by a small amount dr, gets displaced to the right by a small amount dr, then there is work done by this force. Work done by this force, the force is leftwards, the displacement is rightwards. So the work done by the gravitational force is going to be, angle between force and displacements is 180 degrees, so negative work done, so is going to be minus gmm by r squared into dr. That's the work done by this force. But work done by the forces of the field is change in potential energy, is negative of the change in potential energy. Work done by the force of the field is always negative of the change in potential energy. That's how we define potential energy. Work done by the force of a conservative field is negative of the change in potential energy. So when it went from here to here, let's say the change in potential energy was du. For a small displacement dr, the change in potential energy was gu for the particle m, right? So this must be negative of the change in potential energy. This must be negative of the change in potential energy. Clear? That's how potential energies are defined. Which means now, let me cancel the minus signs. Let me integrate both sides. Let's say the potential energy at r equal to r is u. Let's say the potential energy at r equal to r is u. The potential energy when r is r, let's say is, and it's my choice to define a reference for potential. Can I not say that the potential energy at infinity is 0, right? So let's say when r is infinity, the potential energy is 0. Right? Now when I integrate both sides, then the right hand side becomes minus u, where u is the potential energy of this particle at r in the gravitational force field produced by capital M, right? Are you confused? Where? No, I said I have to integrate between limits, right? Huh? I'm saying when R is R, let's say the potential energy is U. When R is infinity, that means when the particle is far away from O, the potential energy is 0. You know what I'm saying? I can always call R equal to infinity as 0 of potential energy. Right? So then, when I integrate both sides, then I get minus U on the left hand on the side, right? Minus U equals minus GMM. When I integrate 1 by R square, I get minus 1 by R, the minus comes out. So 1 by R, R runs from R to infinity, R runs from R to infinity. So now when I evaluate this is 1 by infinity minus 1 by R. This is when R is in, I hope you know how to evaluate these integrals. This is 1 by infinity minus 1 by R, but 1 by infinity is 0. So this becomes minus 1 by R. So this becomes GMM by R. The right hand side becomes GMM by R. The potential energy of this particle at a distance R from capital M, the potential energy of this particle at a distance R from capital M is like a minus GMM by R, is like a minus GMM by R. Potential energy of the particle of mass M at a distance small r from a gravitating mass capital M. That's the potential energy of a mass small m. Are you okay with this? Huh? In fact, yes, please ask if there are questions. Which part? Huh? Okay, the expression was minus u equal to, right, GMM 1 by R, right? R runs from R to infinity. This is, you want to cancel this minus, okay, cancel this minus. So that's going to be GMM into 1 by infinity minus 1 by R, 0, so minus, right? That's the potential energy of a particle of mass m at a distance small r from capital M, right? So, in the field produced by capital M, in the gravitational field produced by capital M, the potential energy at a distance, the potential energy of a mass small m at a distance small r is going to be minus GMM by R. This is for a mass small m. But if small m was 1 for a unit positive mass, for a unit mass, the potential energy is going to be minus GMM by R, right? This is the potential energy of a mass small m. So for a mass m equal to 1 unit, what will be the potential energy at this point P? So potential energy of a unit mass at P is minus Gm by R. This is the potential energy of a unit mass at P at a distance small r away from a gravitating mass capital M. Clear? And potential energy of a unit mass at P is called the potential at the point P. Potential energy of a unit mass at P, potential energy of a unit mass at P is also called the potential of the gravitational force field at P, is called the potential at the point P of the field created by capital M, of the gravitational field created by capital M. The potential at a point P is the potential energy of a unit mass at that point. Potential energy of a unit mass at that point, that's going to be minus Gm by R, where G is the universal gravitational constant, R is the distance from this mass m to the point P, and capital M is the gravitating mass which is producing this field. Are you okay with this? Which we'll henceforth refer to as V at R. Potential would be V at R, which would be potential energy of a unit mass. That's all. Potential at R would be potential energy of a unit mass at R. Clear? Now, there was yet another way of looking at potential at a point, and it will reduce to the same final result, but I'll just state that for your consumption, which is what your school would require essentially. If there was a gravitational field produced by capital M, if there was a gravitational field produced by M, gravitational field means just a field of influence, a field in which another mass would experience a force, another test mass would experience a force because of the presence of capital M. That's a field, right? So, at a point P, write down the potential at a point P in a gravitational force field, the potential at a point P in a gravitational force field is the amount of work done, by an external agent, not by the field, by an external agent. Write down, by an external agent. The amount of work done by an external agent to transport a unit mass, from infinity to P, without adding kinetic energy to the mass, That is, without causing acceleration to the mass, What it really means is, let's say there was a field produced by capital M, and at a distance r, if I'm looking at the potential at r, like I said, is the potential energy of a unit mass at r, which is also defined as the amount of work done in bringing a unit mass from infinity to P by an external agent, very slowly, in the sense without accelerating the mass, without accelerating a test mass, unit test mass from infinity to P. The amount of work done by an external agent is going to be the potential at the point P, and it will turn out to be minus Gm by small r. If you have to bring a unit mass from infinity to P without adding kinetic energy to the mass, if you had to bring from infinity to the point P in an unaccelerated manner, if you had to bring a mass small m from infinity to P without adding kinetic energy to this mass, that is, if it's unaccelerated means its velocity is not changing, that means its kinetic energy is not changing, right? Then the work done by the external agent is going to be the potential at the point P, which is the potential energy of a unit mass, unit test mass, right? Which means work done from infinity to P, by an external agent, kinetic energy remaining constant. That's defined for m equal to 1, That's defined as the potential at R. That's defined as the potential at R. That's defined as the potential at R. It's important that you see, I'll tell you something. If you understand this concept now, this will take care of a large bit of understanding required in electrostats, because the same kind of field, fields, that will also be a central force field, inverse square law field, all the traits that the gravitational force field has. So a good comprehension of this will kind of lessen your load on the electrostatic front. That's the reason, I'm just focusing a little bit more on the basics of gravitation rather than quickly jumping to variation of G with height, depth, color, smell, etc. Right? So then, look, what happens is, there is an external agent, right? When the particle is at some intermediate point between infinity and P, the particle experiences a gravitational pull, experiences a gravitational force leftwards from the gravitating mass capital M, right? So now, what would the external agent do? The external agent would exert at this juncture P prime an equal and opposite force, F external. At every point P prime, if Fg is the leftward gravitational pull, then the external agent must apply a rightward force. Why? Because if it has to counter this force, if it has to bring the particle unaccelerated, that means the net of all forces on the particle must be zero. When can that happen? If at every point the gravitational pull is exactly countered by the force of the external agent, then the net force would be zero, the particle will remain unaccelerated. That means the particle is moved very, very slowly towards P. The particle is moved very, very slowly towards P so that it remains unaccelerated. At every point, all that the external agent does is, it counters the force of the field. It just counters the force of the field. Clear? And in the process, the work done by the external agent will be looked upon as the potential at the point R. Potential at the point R. Right? Now, realize that if at every point, very simple, do you understand that in this transport from infinity to P, the external agent just about applies a force enough to counter the forces of the field so that the particle remains unaccelerated at all times. Clear? Now, in the process, while the particle is getting displaced from infinity to P, there are two jokers working on the particle. One is the external agent which is doing work, because the particle is getting displaced to the left. The external agent is acting rightwards, right? Which means work done by the external agent is negative. Work done by the external agent is negative. Alright. And there is the gravitational force which is acting leftwards, and the particle is also getting displaced leftwards. So this force is doing positive work, right? And for every small elemental displacement, the work done by this is negative of the work done by the forces of the field. Work done by the external agent is negative of the work done by the forces of the field. Yes or no? Right? Which means, from infinity to P, the work done by the external agent would be negative of the work done by the field. Would be negative of the work done by the field from infinity to P. Yes or no? Right? So this would be negative of the work done from infinity to P by the forces of the field. This would be negative of the work done from infinity to P by the forces of the field. That means work done by the gravitational pull. Work done by the gravitational pull. Right? Now, look. When the particle is brought from infinity to P, when the particle is brought from infinity to P, when the particle is brought from infinity to P, then very clearly at every point the gravitational pull is like this, the force because of the field is like this, the displacement is also like this, right? So work done by the forces of the field is positive from infinity to p, so that this entire work done would be negative. That's why you get a negative number for the potential at a point, right? That's why you get a negative number for the potential at a point. Now, do you realize that again, if the particle moved from p to infinity, if the particle moved from p to infinity, then at this point p prime, the gravitational pull will still be leftwards, but the displacement would be rightwards. If the particle moved from p to infinity, if the particle moved from p to infinity, then the work done by the gravitational pull will be negative of the work done from infinity to p. You realize that the work done by the force of the field from infinity to p would be negative of the work done by the forces of the field from p to infinity. Is that all right? Right? So, work done from infinity by the forces of the field will be negative of the work done from p to infinity by the field, right? So, another negative number means work done from, that will take care of this minus work done from p to infinity by the field. Work done from p to infinity by the field, right? That means the potential at the point p would also be equal to the work done by the forces of the field to transport a particle from p to infinity for a unit mass, That's also defined as the potential at the point p. Clear? Now, really then, when the particle, let's say, is at some distance r, then the force because of the field is what? On a unit mass m equal to 1, the force is gm by r squared leftwards, right? And to displace it by a small amount dr, the work done by the field, see, I am taking the particle from p to infinity under the influence of the force of the field, and that will turn out to be equal to the potential at a point p, potential at the point p. Are you fine with these ideas? I hope you are not getting lost in the maze of all of this, right? So the work done by the gravitational pull is like gm by r squared into dr with a minus sign, right? Right? That means the total amount of work done from p to infinity would be sum of all of this, where r runs from r to infinity. I am taking the particle from p to infinity, and for a small displacement dr of the particle towards infinity, I am computing the work done by the force of the field. The total work done by the force of the field from p to infinity would be sum of all of this, where r runs from r to infinity. That's going to be the potential at the point. Are you okay with this? So that's going to be the potential at the point r, which is the potential energy of a unit mass at p, Now, when I integrate this, then I get like a gm 1 by r, see, minus 1 by r, this will become plus 1 by r, r runs from r to infinity. That's going to be the potential at a point r. Clear? Which is like gm 1 by infinity minus 1 by r is like minus gm by r. Clear? So, if I have a point mass m which is producing a gravitational force field, then the potential at a distance r, which is the potential energy of a unit mass when placed at r, is given by minus gm by r. So, if there is a mass small m, then the potential energy of a mass m, small m, would be potential multiplied by small m will give me the potential energy of mass small m. This is potential energy of a unit mass. So, potential energy of mass small m would be this into m, as we have already discovered. Are you okay with this? Do you then precisely understand what it means by the potential at a point? From first principles, we arrived at a result minus Gm by R. Then the other way we could look at it is, it's the amount of work done by an external agent in bringing a unit test mass from infinity to P without causing acceleration, without adding kinetic energy, which in turn turned out to be this, and so on and so forth. So minus Gm by small r is the magic number required. Clear? No confusion on this basic calculation and understanding of potential at a point, right? Now, once you understand this notion of potential at a point, let me again just state one thing for the time being, without giving you much insight into it, is number one, in as far as gravitational influences are concerned, if you had a uniform sphere of mass capital M, if this was a uniform sphere of mass capital M, right, whose center is O, if this is a uniform sphere of mass M, that means same density, same solid sphere, same density. Density is the same at every point. That's what I mean by uniformity. Same density at every point, right? Uniform density, right? Of radius r. Then, for all points P at a distance r, where small r greater than or equal to capital R, for small r greater than or equal to capital R, when would that happen? When the point P lies on or outside the sphere. When the point P lies on or outside the sphere. That means when OP is R, then this entire mass could be replaced by a point mass at the center. That means at O, I can replace this entire mass by a point mass M. And if this is the point P, where if you choose to keep a mass small m, then the force of attraction between small m and capital M is going to be Gmm by R squared, and so on and so forth. So for the sake of gravitational influences, regions outside a uniform sphere, I can replace that entire uniform sphere by a point mass equal to the mass of the sphere at the center of the sphere. Clear? This is one thing. Second thing is, the proof of this is pending. I might have frivolously stated this for a while, but I'll come to this with greater intensity when required, but for the time being, I want you to remember this result, right? The second most important result is, so this was a solid sphere of mass capital M, right? Replaced by a point mass at capital M. We could then have a spherical shell. A spherical shell is like this. Small thickness. This is a spherical shell of a certain mass capital M. Now inside a spherical shell, at any point P of a spherical shell, if you chose to keep a mass small m, if at any point of the spherical shell inside the spherical, this is P inside the spherical shell, this is the point P inside the spherical shell, if you keep a mass small m, then this small m will experience no net force, because of the mass element contained in the shell. Because of the mass element contained in the shell, this small m will experience no net force, will experience no net gravitational force. That's another result, again stated without proof, at least for the time being. Inside a spherical shell, if you keep a point mass small m, then this point mass small m will experience no net force because of the shell. Basically, it can be proved. Proof pending, but then this entire mass capital M could be broken down into several point masses, and the force on P, force on this mass small m at P, because of every point mass could be computed, because of every point mass constituting the shell could be computed. And if you did that, and if you summed up all these forces, we can do that with the help of calculus. Down the line with what's called Gauss's law, we will not even use calculus. I can show that the vector sum of all the forces because of the various mass elements contained here on a mass small m placed inside the shell is going to be, that's important. Now, a consequence of these two results is the following. If I have a solid sphere, let's say, uniform solid sphere of mass m and radius r, O is the center of the sphere. O is the center of the sphere. O is the center of the sphere. Imagine a smaller sphere of radius small r. Inside this, imagine a sphere of radius small r. This is a sphere of radius small r less than capital R. Now, if I placed a mass small m at a point on this sphere, smaller sphere, if I placed a point mass small m, then realize that you would expect the gravitational influence of small m because of the mass inside and because of the mass outside, right? There are two regions, one inside this, one outside this, right? Now, as far as the outside region is concerned, realize that the outside region could be decomposed. The outside region could be decomposed into several shells, infinity of shells, yes or no? The outside region could be decomposed into infinity of these shells. This entire region could be decomposed into infinity of shells, starting from small r equal to small r to small r equal to capital R, from small r radius equal to small r to radius equal to capital R. You will have infinity of these shells, right? Now, for any specific shell, for example, this is a sample shell chosen in the thickness, what would be the force on this mass m because of this shell? 0. Anything inside the shell will experience no force because of the shell. Are you there with me? You know what I'm saying? No. You didn't understand this now. Did you understand the fact when I said that if there is a shell, there is any shell, this is a shell, then a mass placed inside the shell will experience no force because of the shell. I said this a little while ago. Did I say that? Did you understand this? So now, this thickness could be imagined to be composed of several concentric shells. Several concentric shells. This entire thickness could be composed of several concentric shells. This is one particular shell, right? What force will this shell exert on this small m? Huh? Are you totally lost? Huh? Huh? Why? Because of that. That's what I said. Any mass, point mass placed inside a shell will experience no net force. Hey, are you actually listening to me or are you only looking at me? Huh? You're listening to me, right? So this mass small m will experience no net force because of this specific shell, and this entire thickness is like several concentric shells, and each shell will exert no net force on small m. So this entire thickness outside this small r, this entire thickness will exert no gravitating influence on small m. Are you okay with this? Right? Now, force on small m would be because of the force of these several shells outside and because of a sphere of radius small r. Because of a sphere of radius small r inside. Are you there with me or not? Please say that. So, this force is zero. Force because of this is zero. So, the net force that this small experiences is because of this solid sphere of radius small r, because of this solid sphere of radius small r. Are you there with me? Right? If rho is the density of this bigger sphere, then what's the mass of this solid sphere inside? Mass of this solid sphere inside is going to be rho into 4/3 pi r cube. That's going to be the mass of the region inside small r. That's going to be the mass of the region of radius small r inside. Clear? No. Volume into density. 4/3 pi r cubed is this volume into density rho. That's going to be the mass of this. No. That means now this small m lies on the surface of a sphere of radius small r, lies on the surface of a sphere of radius small r, and like I told you a little while ago, this sphere could be replaced by a point mass ms placed at O, right? This sphere could be replaced by a point mass ms placed at O, right? So what's going to be the force that small m experiences? The force that small m experiences is going to be G ms m by r square. That's going to be the force that experiences. Right? Now, m was the mass of the bigger sphere and ms is the mass of a portion of radius small r of the sphere. So, can I not say that the mass will be proportional to the cube of the radius? Mass of any sphere will be proportional to the cube of the radius. So, can I not say capital M by ms? Capital M is the mass of the sphere of radius capital R and ms is the mass of a sphere of radius small r. So, m by ms is going to be r cube by small r cube. Could this be said? This is rho into 4/3 pi r cube. This is rho into 4/3 small. Yeah. So then this force F that this experience is going to be G m by r squared into ms. Ms, like I said, is m by r cube, m by capital R cube into small r cube, m by capital R cube into small r cube. Clear? No? I've replaced this ms from here, m into small r cube by capital R cube. That's ms obtained from this. Are you confused? This is like G mm by r cube into r. So it's the force experienced by this small m if it lies inside the sphere. If it lies inside the sphere, is proportional to its distance from O. Is proportional to its distance from. No? Are you finding it very difficult? I mean, the expressions that you are carrying is one of hatred, vengeance. All of this is going tangential, and some rocket science of a very severe order and magnitude is being hurled and imposed upon you. You like sitting with dead expressions and posing an impediment for me to get into the next level. You don't look fluid in your expressions, causing a burden to me. I don't know. अच्छा, समझ में आया अभी तेरे को बात? पक्का झूठ बोल रहा है? Okay, I'll still try to go as slow as I could. But then there are certain basic things which I cannot avoid. I have to ensure that you understand these things, right? Now, very school related variation of G, right? This is, my dear Earth, mass capital M. I never remember the mass of the Earth, but you have to remember, because you might want to remember, because you will have to appear for exams. I only remember the radius of the Earth, which is like 6,400 kilometers, right? It's approximately spherical, although there is difference between the radius at the equator and the radius on the poles by roughly 21.72 kilometers. That's roughly the difference. But then don't bother about it. In our digressions, basic digressions, we'll assume that it's spherical, perfectly spherical, and that it's of uniform density. First of all, what's acceleration due to gravity? Let's say there is a point mass m at a distance r, placed at P at a distance small r from the center of the sphere, which is the Earth, right? At this point, this experiences a force F. I'm talking of small r greater than or equal to capital R. Capital R is the radius of the Earth. F equal to, now for points outside the sphere, I can imagine this entire sphere to have a mass capital M concentrated at the center, right? I can use that premise. So the force that this mass M experiences is like Gm. M is the mass of the Earth, small m is the mass of the particle, divided by r square, right? Which in turn produces an acceleration on this mass M towards the center of the Earth, which produces an acceleration, right? If a force acts on a mass M, it's going to produce an acceleration. So it produces an acceleration G, which is called acceleration due to gravity at P, for a point at a distance small r, and this point is outside the surface of the Earth. Small r from the center of the Earth. So then this, from Newton's second law, must be mass into G. G is the acceleration for points outside P, on or outside the surface of the Earth, right? So then that gives me G equal to Gm by r squared. That gives me G equal to Gm by r squared. So then for different distances from the center of the Earth, the value of G will vary. Clear? Now, suppose this point P was at a height h above the surface of the Earth, and capital R was the radius of the Earth. Then do you realize that small r is like a capital R plus h? Small r is capital R plus h. So then G for points outside will vary like Gm by capital R plus H whole square, which I can write as Gm by R square. If I take R common, so this will become like a R square into 1 plus H by R to the power minus 2. If I took R common from this, then I have a R square and 1 plus H by R whole to the power minus 2. Clear? Hey, but if you put small r equal to capital R, then you get acceleration due to gravity on the surface of the earth, right? So, if Gs is the acceleration due to gravity on the surface, then Gs is like a Gm by R squared is like a Gm by R squared. So, this I can write as G on the surface of the earth. This is like a G on the surface of the earth, which gives me G equal to G at a distance small r, that means at a height h above the surface of the earth, it's going to be G on the surface of the earth into 1 plus h by r to the power minus 2. Now, one result on generalized binomial theorem. If x is numerically much less than 1, if the value of x is numerically much less than 1, then 1 plus x to the power n is approximately equal to, for any n, it need not be an integer, will be approximately equal to 1 plus nx. If x is numerically much less than 1, then 1 plus x power n will be approximately equal to 1 plus nx. That's an important result. We'll use it like a umpteen times all over, right? Now, there are two possibilities. One, this height h could be comparable to the radius of the earth. In which case h by r will not be small. If this h is comparable to the radius of the earth, for example, it could be r by 2, then it's comparable to the radius of the earth. Or it's like a r by 3, or it's like a 2r, then that's comparable to the radius of the earth, in which case I cannot consider it to be small. But then, if this h is like 100 meters only, then that's really small compared to 6,400 kilometers, the radius of the earth, right? If you raise a particle to a height 200 meters or 300 meters or even a kilometer, then that's much smaller compared to 6,400 kilometers, the radius of the earth, right? So if h is much smaller compared to the radius of the earth, right? If h, the height to which it's raised, is much smaller compared to the radius of the earth, then this is approximately Gs into 1 minus 2h by r. That, no? 1 plus x. If h is much smaller compared to r, that means h by r would be numerically much less than 1. If h is much smaller compared to capital R, then h by r would be numerically much smaller than 1. So then this is 1 plus x to the power n, which would be approximately equal to 1 plus nx, where n is minus 2. Right? So now this will always be good, but this equal to this would be good only when h is numerically much smaller compared to the radius of the earth. Right? So now that's how G varies from the surface of the earth, etc. That means let's say this is the center O and this is R. This distance is R. R equal to 0 will mean the center of the earth. Small r equal to 0 will mean the center of the earth. Whereas small r equal to capital R will mean the surface of the earth. On the surface, let's say the value of G is Gs. On the surface, the value of G is Gs. And what we worked out is G equal to Gs, Gm by R square, right? G equal to Gm by R square the result that we got was G equal to Gm by r squared. That's what we got, right? G at a distance small r. That means at a distance small r, where r is greater than or equal to capital R, if you increase small r, G decreases. So from this point, from the surface of the earth, if you increase small r, the value of G decreases. The value of G decreases. It decreases as 1 by r squared. It decreases as 1 by r squared. From the surface of the earth onwards, if small r increases, the value of G decreases. It falls as 1 by r squared. It falls as 1 by r squared. Clear? So that's a variation of G from the surface of the earth onward. From the surface of the earth onward, that's how small g varies with distance from the surface of the earth above the surface. Right? Now, inside the surface, let's see what happens when small r is less than capital R. If I place a mass small m at a distance small r, where small r is less than capital R, that means I want to find acceleration due to gravity at distances small r less than capital R. That means for points inside the surface of the earth, I want to find the variation of G with the distance small r from the center of the earth. Very clearly, this mass small m will experience a force towards the center only because of this mass, right? And this mass is like mass small ms, is ms. It experiences a force towards O, which is G m ms by r squared, like I said. That's a force that this experiences because of this mass, and the force that this experiences because of the mass outside is 0, right? And this could be written as Gm by r squared. Now ms, if m is the mass of the earth and ms is the mass of this smaller sphere, then ms by m, like I said, is going to be r cube by capital R cube, will be proportional to the radius, right? So I could write this ms as m by r cube into small r cube, which is like Gmm by r cube into small r, Gmm by capital R cube into small r, right? That's the force that this experiences, and this must be equal to mass into acceleration due to gravity at small r. This must be mass into acceleration at small r, right? Which gives me G equal to Gm by r cube into small r, Gm by r cube into small r, where Gm by r cubed is a constant. R is the radius of the earth, capital R, capital M is the mass of the earth, G is 6.67 10 to the power minus 11. So then this G is proportional to R. That means at the center of the earth, small r is 0, it's going to be 0. And as you keep moving further and further away from O, then G would increase proportional to R. That means G versus small r inside the earth would be a straight line, yes or no? G versus small r inside the earth will be a straight line, isn't it? Y equal to mx, y equal to mx kind of a thing. So inside the earth, at small r equal to 0, g is 0, and then it increases linearly with distance small r from the center of the earth. Clear? So that's a variation of g. Inside the earth, from the center to the radius of the earth, it increases linearly, and then from the radius of the earth above the surface, it falls like 1 by r square. That's the variation of g with height, depth, etc. Clear? Now, because of rotation of the earth, this is the earth, this is the center of the earth, and this is the equatorial plane. This is the equator. All of you know what an equator is, right? Hey, in geography, I never understood equator, but when it came in physics, I understood. They kept saying equator for years in junior class, right? And I always ignored whatever it is. Who cares? What's equator? What's latitude? What's longitude? Actually, never understood. But the moment it came in physics, I understood that. Because it took me a long time to understand what an equator is, what poles are, what latitude is. But I'm sure you are smarter kids. You would have understood equator in geography, right? So in any case, that's the equator. This is the equatorial plane, right? This is the center of the earth. Huh? This realizes the North Pole. This is the South Pole. And the earth revolves around this line, rotates around this line, spins around the ns line, with an angular speed omega. The earth is a rotating frame of reference. Now, to complete one full spin, it takes 24 hours. To complete one full spin, it takes 24 hours. You understand that too, right? Huh? That means it describes an angle 2 pi in 24 hours, right? So the time period is like a 2 pi by omega. Omega is known because capital T is 24 hours or 86,400 seconds, right? So from that, the omega can be known. From capital T equal to 24 hours, you can calculate the angular velocity of spin of the earth about the ns axis. Clear? Now, for a particle here, for example, the latitude of this particle is given by this. This is the latitude of the particle, lambda. This is the latitude of the particle, lambda, right? Now this particle P moves in a circle of radius small r. This particle P moves in a circle of radius small r. This particle P, isn't it? While this spins like this particle P, this point P moves in a circle of radius small r, in a circle of radius small r, and by the time the Earth completes one full spin, this particle completes one full circle of radius small r, completes a 2 pi small r, right? That means the omega for the Earth is the same as the omega for this particle, because they describe the same angle in the same time about their corresponding centers. If you have to compute the omega for this, realize that this will also take 24 hours to complete a full circle. So the time period T and the omega for the Earth and for this P is going to be the same. No doubt on this? Huh? One thing which you will have to gleefully accept from me right now, in a rotating frame of reference, we have what's called a centrifugal force, which is a radially outward force that this particle P experiences. I know I haven't given you enough joules, but then at least a makeshift arrangement for the time being. This particle, this point P, this particle, let's say mass small m, experiences a radially outward force which is called a centrifugal force, small m omega squared small r. Clear? Where realize that if this angle is lambda, this angle is also lambda, this angle is also lambda, this angle is also lambda, this is capital R, right? Now at this point P, the particle of mass small m experiences a normal reaction from the Earth, experiences a normal reaction from the Earth, from the surface, right? Right? Because of the gravitational influence, if g was the acceleration due to gravity at this point, if g was the acceleration due to gravity at this point, effective, g effective was the acceleration due to gravity, then it experiences a force mg prime, mg, where g is the g effective here, is the g effective here, then the gravitational pull will be mg, the reaction from the surface of the Earth will be n, mg will be the gravitational pull, where g is the g effective, right? The particle will experience a centripetal force m omega squared r like this, as we've discussed earlier, centrifugal force outward. The centrifugal force has a component here along n and has a component tangential, right? The tangential component of the centrifugal force is balanced by friction. This is tangential component of the centrifugal force Ft, of the centrifugal force Ftc. Tangential component of the centrifugal force is balanced by the frictional force. Now, mg is the force that would be acting on this particle if there was no acceleration due to gravity, if there was no acceleration due to, if there was no omega, if there was no omega, if there was no spin, then g was the acceleration due to gravity. Let's say g was the acceleration due to gravity if there was no spin, if there was no omega. Now, if N was the force, that this exerts, then realize that this particle P with respect to the earth is stationary. That means net of all forces acting on it must be 0 in this direction. In the radial direction, the net of all forces acting on it must be 0. That means N plus m omega squared r cos lambda must be mg, where g is the acceleration due to gravity in the absence of omega, is the acceleration due to gravity in the absence of omega. So we have m omega squared r cos lambda plus n, that's equal to mg. N, the normal reaction from the earth, is going to be m into g minus omega squared r cos lambda, where g is the acceleration due to gravity when omega was 0. G is the acceleration due to gravity at P when omega was 0. If the earth was not spinning, then this would be the acceleration due to gravity. Now, because of the spin, let's say the acceleration due to gravity is g prime, then the earth actually exerts a force mg prime like this on the particle, right? And should that not be equal to n? Should n not be equal to m into g effective? Should n not be equal to m into g effective? Right? You know what I'm saying? Should n not be equal to m into g effective? So replace this n by m into g effective. So G effective is G minus omega squared r cos lambda, right? Hey, but small r is capital R cos lambda. See, the small r is capital R cos lambda. Small r is capital R cos lambda, yes or no? Lambda is the latitude of the point. At the equator, lambda is 0. In which case, G effective becomes equal to G. The effect of omega is not felt at the equator, because at the poles. At the poles, lambda is 90 degrees. So cos square lambda will be 0. So G effective will be the same as G. So the effect of lambda is not felt at the poles. The rotation of the earth is not experienced at the poles, but at the equator. Lambda is 0, cos square lambda is 1. So then the effect of omega is most pronounced at the equator, where lambda is 0. So this you might want to write as G into 1 minus omega squared r by G cos squared lambda, where lambda is the latitude of the point. So this will give you variation of G with latitude, where this G is the G when omega is 0. This is the G when omega is 0. The earth was not spinning, then this would be G. But now if the earth was spinning, the G effective would be the G when earth was not spinning minus omega squared r cos lambda, and so on and so forth. The variation of G with latitude is this. You might want to remember. Clear? And of course, the next variation is, which we will not document mathematically, but we have to understand that qualitatively, the G on the equator is different from G at the poles because of the difference in the radius of roughly 21 kilometers between the pole and the equator, right? So that's another variation, primarily height, depth and rotation, right? These are things that will be required for yours, right? Not a problem, right? Now, some important numbers for gravitational fields, some very important numbers for gravitational fields. Let's say this is the Earth origin, radius capital R, and let's say there is a satellite orbiting the Earth at a distance small r from the center of the Earth. There is a satellite of mass small m. Mass of the Earth, let's say, is capital M, and that's orbiting the Earth in a circular orbit. Let's say it executes a circular orbit around the Earth. If V0 is the speed of the satellite, then to execute a circular motion of radius small r, it will require a centripetal force, which would be how much? mv0 squared by small r. And who would provide this centripetal force for this circular motion? The gravitational force between the Earth and the particle, between the Earth and the satellite. The gravitational pull will provide this required centripetal force. So then the mv0 squared by r is the requirement and is met by this, where V0 is the speed at which it executes this circular motion, uniform circular motion. This V0 is called the orbital speed of the satellite. It's called the orbital speed of the satellite. Orbital speed in a circle of radius small r, that's the orbital speed of the satellite. V0 then becomes like a root gm by small r. V0 then becomes like a gm by small r, the orbital speed. The total mechanical energy. Now this satellite at this point has kinetic energy half mv0 square and also has potential energy, which is minus gmm by small r, which is minus g capital M into small m by small r. That's its potential energy. So the total mechanical energy TME, the total mechanical energy of the satellite will be kinetic plus potential, right? Kinetic energy plus potential energy. That will be the total mechanical energy of the satellite, right? Which is going to be half m v0 squared minus gmm by small r. Hey, but as you can see from here, half m v0 squared is like gmm by small r. Half m v0 squared would be gmm by small r. So this is like a gmm, half of gmm by small r minus gmm by small r. So that makes it minus half gmm by small r. That's the total mechanical energy of the satellite, right? So this is another result that you want to remember for a satellite having an orbital radius small r, the total mechanical energy is minus half gmm by small r. Right. One fact which you might want to bear in mind for the time being is, if the total mechanical energy in a gravitational field of a entity is negative, which means it's present in the field. Total mechanical energy negative means it's bounded to the field. Total mechanical energy negative would mean that it's bounded to the field. The particle is bounded to the field, it's present inside the field. Negative mechanical energy means its boundedness in the field, its boundedness to the field. Right? If the total mechanical energy becomes zero, that means it's escaped from the clutches of the field. It's not prevalent inside the field. Right? Because if it's present inside the field, even if it does not have kinetic energy, it will have potential energy. Right? Which would be negative. Right? And the moment it escapes to infinity, right? For sure, kinetic energy could either be zero or very large. Kinetic energy could either be zero or very large, very far away, and potential energy is zero. So very far away from the field, the total mechanical energy would either be zero or positive. But inside the field, the total mechanical energy ought to be negative. That would cause boundedness to the field. That will cause boundedness, right? So this is one fact that you might want to remember. Minus gmm by 2r, orbital speed root gm by small r for a satellite orbiting in a radius small r around the Earth. Now another important cosmic velocity. These are all various cosmic velocities, orbital speed, and yet another cosmic velocity which you might want to remember is the following. The Earth at a distance small r from the center of the Earth, I impart a certain velocity, call it Ve, I impart a certain velocity to the particle so that it escapes from the gravitational field of the Earth, right? That means it moves on to infinity, right? Now, at a distance small r, right? At a distance small r, the total mechanical energy is going to be minus gmm by small r, right? The kinetic energy is going to be half m Ve square. That's the total mechanical energy. At this point, minus gmm by small r is the potential energy, half m Ve square is the kinetic energy. When it escapes to infinity, potential energy becomes zero, and let's say kinetic energy also becomes zero, right? Let's say kinetic energy also becomes zero. When it escapes to infinity, the potential energy becomes zero, and let's say the kinetic energy also becomes zero. That means at infinity, potential energy is zero and kinetic energy is zero. Now, this is conservation of energy between this point and infinity, which would give me V epsilon equal to Ve equal to root 2gm by small r, right? Which means if you impart at a distance small r from the center of the Earth a velocity equal to Ve, the particle will escape the gravitational pull of the Earth. It will move on to infinity, and by the time it reaches infinity, it would be dead on its kinetic energy front, right? But if you provide a velocity greater than the escape velocity, it will still escape to infinity, but will have some remaining kinetic energy, right? So the minimum velocity that you must impart to a particle, so that it could escape to infinity is root 2 gm by small r, which is called the escape velocity. The more the merrier. If you impart it a velocity greater than the escape velocity, then also it will escape, but it will follow a different trajectory. So this is the escape velocity, minimum velocity that you must impart so that the particle escapes the gravitational pull of the which means now another number which you might want to remember, if small r is capital R, then the escape velocity, then that's the escape velocity from the surface of the earth, right? If small r is capital R, then V escape on the surface of the earth, that will turn out to be 11.2 kilometers per second. This number will turn out to be 11.2 kilometers per second. That's the escape velocity from the center of the earth, from the surface of the earth, from the surface of the earth. 11.2 kilometers per second. Now, couple of more results. So this very clearly is root 2 times the orbital velocity. Do you realize that? The escape velocity is root 2 times the corresponding orbital velocity. Root 2 times the corresponding orbital velocity. Again, a set of things which you might want to carry in your heads. But again, a detailed discussion is prohibitive at this point of time. This is the earth, center of the earth, and let's say there is a particle at P. At P, you could give the particle, and let's say P is at a distance small r, you could give the particle an orbital speed. You could give the particle an orbital speed. If you give it an orbital speed, let's say you give it a velocity v. If v is v naught, the orbital speed, the particle will move, will have a circular orbit around the earth, will have a circular orbit around the earth. If v equals escape velocity, if v is escape velocity, the particle will get itself freed from the clutches of the gravitational pull, will escape to infinity, and the path that it would undertake, see one thing, so when v is v orbital, then it will go along this. If v is v orbital, this is the case where v is v orbital, right? It will take up this path. When v is v escape, then if v is v escape, then it will undertake a parabolic trajectory and escape to infinity. It will undertake a parabolic trajectory and escape. And if v is greater than v escape, then also it will escape to infinity, but it will undertake what's referred to as a hyperbolic trajectory. I will just have a few more remarks, but let me see if I have space around this. It will take a hyperbolic trajectory. If v is greater than v escape, it will undertake a hyperbolic trajectory in order to escape to infinity. If v is v escape, it will take a parabolic trajectory to escape to infinity. Now, v could be a number lying between v naught and V epsa. V could be a number greater than the orbital speed but less than the escape speed. V could be a number, you could impart the particle a velocity V which could be greater than the orbital speed but less than the escape velocity. So then when at least I give you a reason to cheer. This, if V is greater than the orbital speed, less than the escape velocity, it will not escape, but it will not be in a circular trajectory. It will not escape because its velocity is less than, and it will still not be in a circular trajectory. What it would do is, it will undertake what's called an elliptic trajectory. It's called an elliptic trajectory. It will undertake an elliptic trajectory around the Earth. Elliptic trajectory. V is greater than the orbital speed but less than the escape velocity. It will execute an ellipse. It will execute an ellipse with the center of the Earth being one of the foci of the ellipse. I know you don't understand anything about ellipses, but then for the time being, make a note of it. It will execute an elliptic trajectory with the center of the Earth being one of the foci, for the, right? And so this is V greater than V naught and less than V. If V is less than orbital speed, if V is less than orbital speed, right, V could have been less than orbital speed, then what would happen is, it will again take up an elliptic trajectory, but it would want to undertake this full trajectory, but it would hit the surface of the Earth prematurely. It starts on the premise of an elliptic trajectory, but hits the surface of the Earth premature to its execution of the complete ellipse, premature to the execution of its complete ellipse. That is when V is less than the corresponding orbital speed. It would want to execute an ellipse, but will hit the Earth at some point, right? If V is equal to orbital speed, circular orbit. V greater than orbital speed but less than escape velocity, elliptic trajectory. And V equal to escape velocity, parabolic escape. V greater than V escape, hyperbolic escape. That is what happens, right? These are things that you might want to remember. Clear? Now, like I said, obviously all that I'm providing to you at this point of time is what you require directly for school, right? So I'm not offering to give you anything which is very genuine. What I'll do is, and again, since I have not taught ellipses, I can't give you a very authentic treatment on this entire subject. I mean, I'll always do a patch-up operation here and there and try and offer things too, so that, you know, at least you look intelligent enough to solve a few problems on gravitation in school, right? You understand what how G varies, you understand what potential energy is, you understand what orbital speed is, you understand what escape velocity is. Now, one more thing, there are a few more things, but at least one more thing which I want to deliver before I call it a day is the following, which is called a geostationary satellite. Geostationary satellite, that's one thing which again they want from you in school. Hello? Don't get fidgety, please. This is the equatorial plane. This is the equatorial plane. Now, very simple. The Earth spins around this ns axis with an angular speed omega commensurate with time period equal to 24 hours. R is the radius of the Earth at a height h from the surface of the Earth. If you impart a particle a certain velocity so that it moves in the equatorial plane, with an angular speed same as that of the Earth, right? At a certain height h above the surface of the Earth, if you cause a particle to move in a plane same as the equatorial plane, right? This is the equatorial plane. If you cause the orbit to be the equatorial plane, right? This entire thing is the equatorial plane, but in a different radius than the radius of the equator, such that this particle takes 24 hours to execute a full circle, such that this particle takes 24 hours. This satellite takes 24 hours to execute this circle in the equatorial plane. Then do you realize that with respect to a certain point on the equator, it will always be stationary? If the omega of this is the same as the omega of a point on the surface on the equator, then the amount by which this gets displaced is the angular displacement of this, and this point P will always look directly above this point Q. So P and Q would be stationary with respect to each other, and that's a geostationary satellite. So in a geostationary satellite, essentially, what's omega? Omega is 2 pi by, where T is 86,400 seconds or 24 hours, right? And the centripetal force, m omega squared small r, where small r is capital R plus h. The centripetal force is provided by the gravitational pull from the Earth, gmm by r squared. So if you plug in omega equal to 2 pi by t, where t is known to you, then you get the radius r of the orbit of the satellite. From this equation, you can solve for small r, the orbiting radius of this satellite, this geostationary satellite. Do you realize what I'm saying? This is the radius of this geostationary satellite. It has to be right above the equator and imparted a velocity such that its angular velocity is the same as omega of the Earth. Then this will be a geostationary satellite. Clear? This is all that you need to know on the geostationary satellite front. So by and large, now one last thing which is pending, which we'll discuss when we meet on Sunday, the Kepler's laws, right? Those are Kepler's laws. Just in case, you could just read a couple of pages of ellipse from textbook. It could help. Even if you don't read, don't worry about it. I'll give you a quick 15-minute crasher on what you need for an ellipse before I don't want to give that to you right today, because you're already mentally fatigued by this time, and any offering which is relevant might go waste. So I don't want to add more burden for the day.